Okay, so we can start. Michael's here. Yeah, sorry about the delayed start, but anyway, we're getting there. Just a reminder about the text, and as Michael said, I'll try and make a better connection between what's happening in the text. What I probably should do is just have a review section in each lecture with the homework. But let me think about that, and I'll try and make a change for next week. Okay, so I think I had to. I've got to move these on, but that's where we are, October 23rd. It's gone away again. And I don't have anything particular there. That's what we're doing. I haven't added anything to the project ideas. I think I may do something a little different with the project, but we'll see how we go. I might choose one and then, or maybe two, and get groups to do that. But we'll see how we go. So I have a bit of stuff today. A couple of weeks ago I talked about recursion in Vhdl, and I wanted to briefly talk about that today. For Lab 8 and the subsequent labs, I've talked about how mechanical switches don't give you a clean 1-0 transition, right? They chatter. And so I wanted to show you some code that debounces those switches. And that's that piece. And then there's labs. I want to give an overview of Lab 8. I want to finish Lab 6 if you haven't already, and start Lab 7, which is the up-down counter. So for the midterm so far, I have had 5 people take it. I haven't graded everyone yet. I think I'm missing 2 people. But I had other stuff to do yesterday, so I didn't quite get there. And so far, I'm mostly happy with the answers. But yeah, I'll once everybody's taken the midterm, I'll give a lot more detailed feedback about the answers that I was expecting. So, recursion in Vhdl. Remember, recursion is where, I probably should have put a definition, right? Recursion is where you have a function right, and there's a condition, and one condition makes, I don't know, a self-call back right? So recursion is the fact that you're calling the function itself from within the function. Okay? And the the issue with recursion is if you didn't have this else condition, the return for, I just said x, but for some value, that doesn't call the function itself. If you don't have that condition, then you get effectively you get an infinite loop, right? And you've probably heard the term stack overflow. When a function is called, the information for that function call is pushed onto the stack, right? The stack is a memory device that computers use. The two main ones are stack and heap. So if you don't have that return condition, it's called the base case. If you don't have that return condition, then memory keeps getting allocated on the stack and is never released. And depending on which way you draw it, the stack grows and the heap comes down, or the other way around. And if those two ever meet, that's a problem. If the stack grows beyond bounds, then that's called a stack overflow. So the important thing is to have the exit condition, or it's, as I said, it's usually called the base case. Now, Vhdl allows a level of recursion, but you need to be very careful with it, and because remember, Vhdl is not executing on a general computer, so it doesn't have a stack with on a full gig of RAM, or a 80 or a 16 gig of RAM, whatever it is, to take up that stack allocation. So when the Vhdl compiler, Quartus, goes through, it has to elaborate exactly how big that call stack is. It needs to allocate an adder or a subtractor or a lookup table or whatever. It needs to allocate its own resources to implement that function, as deep as that function is ever going to get. Because if it can't, it can't implement it. So yes, while Vhdl does allow recursion, it has to be able to be explicitly enumerated, and it has to be quite finite, depending on the size of the device you're trying to deploy it to.
So you put on a small machine that doesn't have enough resources.
It may not have enough resources, and the compiler will tell you that. Okay?
Or like there's not really a need for it.
Usually there's not a need, right? I could make up examples, but they're mostly just make believe. They're not real. So, in fact, I tried to put together an example, but I didn't quite get there. So one piece that I haven't gone through with you yet, that I probably should go through. You saw in the 4-bit adder subtractor how to create a component, right? An instance of a component. So you had your separate full adder device, and you saw how to add an instance of the 4 instances of the full adder in your 4-bit adder subtractor. That was easy enough to do. you might imagine that there's sometimes devices that are much more complicated than just creating 4 instances. And there exists what's called a generate statement in VHDL, and I'm not going to talk about that specifically today. I'll talk about it next week. But what it lets you do is generate huge arrays of instances of components, potentially huge arrays, programmatically. So you can effectively put the instantiation of a component in, for example, a for loop, right? So instead of just creating, cutting and pasting 4 different instances like we did in the 4-bit adder, you could put it in a for loop and create 1,000 of them, or 10,000 of them if the device would take it. The place I've seen, at least in examples where recursion is used, is often in that generate, because often the structure of the device is in terms of the instances and how the different instances of components are connected together can be expressed simply in a recursive manner. And provided that recursion is small enough, the base case exits soon enough, then the compiler can instantiate all those devices using that recursive approach rather than a direct approach. Right, and the main thing to know is, yes, it's possible. As I said, the key is to stop it going wrong. Make sure you have a base case. And the Quartus doesn't seem to be too bad at flagging when it can't instantiate the what you're trying to tell it to do. But some tools aren't great at it. Okay. So let's see if we can make that a bit smaller so I can put it on the screen. Maybe one hit. There we go. Maybe not. So as I said, right, if you've got a mechanical switch, right, something like that, or maybe something like that, right? What happens with the voltage is not that. That's not what happens. What happens, or usually, is there's chatter or bounce. And we have to deal with that if we've got a push button that we're expecting a user to use, because you don't want to count lots of bounces. And it's going to be particularly important in the baseball counter that we're going to be doing soon. So I thought I'd just go through and show you a way to do it. Right, so here's let's just zoom in on the entity statement first. Right, so here's an entity statement for a debound switch. And you'll notice the first entry is a clock, because often when you want to debounce switches, you want to use that input into some sort of a clocked signal. So we're going to make use of that in this. So the other thing, the way we're going to do it, right, is the way you debounce a switch is you say, okay, is there a blue one? There's a blue one. Right? If the switch is high for some known time, or stays high, then we're okay. So here it hasn't stayed high, it's dropped low again. But then we move on a bit further, and now it's high all the time. So we want to count for a certain duration, and we want to say, okay, it's high, so, and it's been high for long enough, so we're actually going to pass on the fact that it's high. So the entity statement, we've got that clock. We're going to use that clock to count the time. Right? And the input, that's the switch that's bouncing around. The output is the debounced version. So let's have a look at the architecture. First of all, we've got a debounce count. And what is it? It's 5 million. That's quite big. But I don't know if you know, but the boards we have, the clock frequency is 50 megahertz. Right? So if we're going to make a count of 5 million, that's only 0.1 of a second. That's only 100 milliseconds, which is still pretty quick. Right? What we don't want when we're pressing that button, probably, it depends on the application, but you don't want somebody to have to hold the button down for a second to indicate a ball or a strike or a new batter. And then we have a count, and we have a state. Right? We want to decouple the input value from the thing that we're outputting, and we want to keep a knowledge of the previous value, which is what that state variable is going to do. And then we have a process, and where our sensitivity list just depends on the clock. Right, so we're only going to do something when the clock changes, and in fact we're only going to do something on a positive clock edge. Right, so that's a positive edge. Then if the state is not equal to the input, so we're changing state, and our count is less than, our counter variable is less than the debounce count, our 5 million, and there's been a change in the input, then we increment the count, and then we exit. If none of that is true, if we get to the debounce count limit, then it's been high for long enough, so we output we zero out the counter, and we take our input and transfer it into the state. And if everything else is true, then we just zero out the counter, we start the counter again. So that means we've had some chatter. And then the last thing we do, remember this is now outside of the process statement. So this happens all the time. We just take the state and shove it to the output. We just connect it straight to the output. So anytime the state changes, we see that. Okay, and that will debounce the switch. So there's two pieces. There's the process that tells you, that counts how long the changes come in, and then there's the wiring to connect the state to the output. Any questions about how that works? Is that okay?
And is this for the lab after lab 7?
Yeah, this is for lab 8. I don't know what does that. So I talked about the 7-segment encoder last week. Just a reminder that there's two pieces to it. The first one is here. It's right. You've got to select the appropriate digit. And then the other piece is to light the digit up. Both of these, the switch debouncer and the 7-segment decoder, you're going to have to use in Lab 8. Right, so I don't know how many people here are familiar with baseball. I know I've had classes in the past where somebody hasn't known, so I thought I should explain what we're trying to do, even though I'm not going to explain the game. But the piece of the game that this counter is aimed at is to keep score of what's happening with the batter. And the batter can do, well, lots of things, but the things we're interested in is they can have a strike awarded against them, which means they should have been able to hit the ball and they didn't for whatever reason. And we need to count those, and that's where the phrase 3 strikes and you're out comes from. Right? So we need to count up to, well, 3, but then once 3 is up, we have to reset the counter. If the pitcher doesn't throw the ball properly for whatever reason, then that is called a ball. Right? And once a pitcher throws 4 balls, then the batter will be able to walk to first base. Right? So we need to be able to count up to 4 on the ball counter. But once it reaches 4, we reset because it's a new batter. And the third button is, it may actually happen that the batter hits. And in that case, there's a new batter. And so we want to also reset the count. Now there's two counters. There's the ball counter and the strike counter. And if either one of them is reset, we want to reset both of them. So the ball counter getting to 4 will reset everything. The strike counter getting to 3 will reset everything. And hitting the new batter button will also reset everything. Now if you've ever played with a real one of these, there's lots of other bells and whistles. You can usually increase or decrease the strike count, or increase or decrease the ball count, or do all sorts of things. But this is really simple. There's 3 buttons, and we're going to make the leftmost 7-segment display on the board display the number of balls, 0, 1, 2, or 3. Remember, once it hits 4, it resets. Once it hits 4, the LEDs are flashed twice, and the counters are both reset. The rightmost 7-segment display, so remember there are 4 7-segment displays. The leftmost is for the balls, and the rightmost is for the strikes. And it will only show 0, 1, or 2. And once the strike counter reaches 3, the LEDs are now flashed 3 times, and again both counters are reset. Okay, now we have to put this into an entity. So this is the sort of stuff that we're going to need. We're going to need a clock, a ball counter input, a strike counter input, a new batter input. Remember, we need to select which digit. So we need to output that. We need to output the digit for the 7-segment display, and we need to be able to flash the LEDs. So we've got 4 inputs if we're not self-generating the clock, and we've got 4, 7, 4, what's that, 15 outputs in order to drive the system. Let me see if I can pull up the video of one of them working. Maybe. I think I added it to this semester's playlist. Let me just check that. Maybe I didn't. Let's see if I can open up the PowerPoint, get that link. Just go with the Adobe. I'll see if I can play the video. No, just thinking about it. I think I need a new computer. There we go. Let's see if that plays.
So this is the ball counter. And
Yeah, so that's the ball counter,
is the strike counter.
and the right hand one is the strike counter.
Is
Let me see if I
the new batter
turn the light off, replay it, you see.
and it'll also reset once I go with the strikes. New batter. New batter. It seems to be doing the right thing.
Okay, let's just try that again. And you,
So this
I don't
is
think
the
the LEDs
ball
flash
counter.
for this version. I think this was an earlier
And I
version.
can increment that.
Yeah, the
Is the
LEDs down
strike
here
counter.
don't flash, but they should be flashing. I think the version I have on the board,
Is
I have put on the board,
the new
they flash.
reset. And it'll also reset once I've gone with the strikes. New batter. New batter. So it seems
Okay.
to be doing
That's
the
what
right
we're
thing.
aiming to do. Let me just put that into Discord channel if it's open. Okay. Any questions about Lab 8? That okay? Okay, so aim today is to finish Lab 6 if you haven't already, and hopefully finish Lab 7, or at least get it most of the way underway. So remember the lesson from Lab 6, right? One lesson you should take away from Lab 6 is that Vhdl allows you to do stuff much more simply or directly than MSI or LSI chips, right? The having to use a full adder and put together 4 full adders to add 4 bits to
Okay,
it.
this is a quick showing about how to run quarters
Sorry,
and models.
let's kill that. There we go. And I suggest you have a look at that link. I'll post that link. I'll copy and paste that link into the lab so that you can have a look at it. And this is just a simple example of a counter. But that page has about 13 or 14 different examples of counters. Don't think any of them specifically actually do what the lab asks you to do, but they should be. Most of them are pretty close, so there's not a lot of difference between. Okay, any questions? Let's get the lab done. And this lab, I would like you to, I think it asks you to put it onto the board and to connect the lower 4 bits. It's asking you to make an 8-bit adder and connect the lower 4 bits to the 4 LEDs, so we can see the counter change. Okay. Let me
lab.
that leaves.
Oh, yeah.
Well, it's the one that leaves.
I thought we
Yeah,
could
it leaves too.
find it.
I'll be back.
So you're gonna make this due next Saturday?
Yes, that's the aim. Is it due
So,
next Saturday? I thought I'd set it up appropriately, but maybe I missed it. No, I hadn't changed it. I'll set it to due next Saturday. And if you need help, would you mind using the help link at the top of the lab setting, just so that I make sure I get to everyone? You can either click on the words that say help queue, or you can use the QR code to get access to it.
What was the board's name? Or,
Sorry?